Watch Mr. Wizard. That's what all the kids in the neighborhood call him because he shows them the magic and mystery of science in everyday living.
Oh, hi, Alan. Come on in.
Hi, Mr. Wizard.
Hi. See what I have projected on the card over there?
Uh-huh.
What does that look like?
Looks like a drop of water.
That's right. That's what that is. That's a drop of water, very highly magnified, and that is going to help you understand how you're going to solve a matter of life or death to you before you leave.
To me?
Right, because that has to do with molecules, and that's what we're going to investigate today. And you're going to have to make an important decision based on molecules.
Okay.
Right? Here, I'll show you what the problem is. Come on around over here. See that glass over there?
Yeah?
Well, take a look at that glass. Right now it's empty, all right?
Right.
But here is a fruit drink, and I'm going to fill that up to there with the fruit drink. Unfortunately, I want it to be grape.
It doesn't look grape.
It isn't grape, no. But I'm going to make it the color of grape by putting either A or B into it. Unfortunately, one of those is ink. And let us pretend that it is a deadly poison. If you drink the ink, you turn purple.
Uh-oh.
The other one is ordinary food coloring, so it would be perfectly all right to put it in here. The problem you have to decide is which is ink, which is food coloring, A or B, and you have to put it in here, and before you leave today, you have to drink it.
I'll have to drink it.
Yes.
All
Which is
right.
which?
Let's see.
What are you doing, drinking?
No, I'm smelling it.
Oh.
Doesn't smell any different.
Okay, well now, maybe I can give you a couple of hints. And what you are going to be is an analytical chemist as you do it, because you're going to try to analyze these two.
Uh-huh.
And one of the ways an analytical chemist would do this is by a technique called chromatography,
Chromatography?
coming from the word color, chrome. Here, I'll show you what we'll do. Here we'll take ink, something that we know for sure. And if you take a piece of paper toweling and roll it into a tube like this, you see, I have marked ink on the top. See? Now you take a pen, or better yet, a little brush, dip it into the ink like this, and about an inch or so from the end of the paper tubing, you draw a line like that. See?
All the way around?
All the way around. Now wash off the pen, we can get rid of the ink. Now you see these jars I have back here?
Yes.
Here's one labeled ink. In the bottom of that jar is a solution. 5 parts of water, 1 part of alcohol. We now put this in here like that, and it'll stand there. Okay? And the water and alcohol solution is now going to rise up into the paper. Okay?
Uh-huh.
Now let's do the same thing now with food coloring. Red and blue to make a nice dark purple. This is the stuff they use for making cakes and things, you know, making colored
Yes. Good color.
cookies and things like that, frosting. Okay, we'll stir that up to make sure it's a nice... And we take that same pen, and here I have another one of those pieces of paper towel rolled up, marked food color, see? Do the same thing. Now, what we're going to do is we're going to let this alcohol and water combination that we have over here separate these things for us. There's the jar marked food, and here's the... Now, the chemicals in these two colors are going to be separated by the liquids as they go up.
Into the paper towel.
So you can now see that all you have to do is do this with A and B, and you'll be able to compare it with what you know as ink and know as food coloring, and you should be able to make a decision.
Yeah.
Okay, so you do the same thing that I just did here with A and B. Here's a paper towel marked B, and another one marked A. So you go ahead and do the same thing.
Alrighty.
Now, pay close attention to what you're doing here, because I think you'll probably want to do this at home. It's a lot of fun because, go ahead, the patterns that you get when you finish are in very beautiful colors so that you can make a nice design. Ooh. I think I'll just put this over here if you don't mind, so you don't mix A and B together. You won't know what to take. Because as a result of this...
That's A.
That's A. Okay, here's B. You see, I'm putting it in A, so I don't want you to accuse me of having switched them or anything. All right? There goes an A. There's B. Oh, did you wash it off?
Yeah, I washed it
Okay.
all the way around. There.
Okay, we put that in B. Now, take that one out and tell me what's happening to it, the one we've started with there. You see that?
Yeah, it's changing colors. Down below, it's sort of purplish. And then up top, there's a bend of green.
I thought we put black ink in there.
We did. But
We-
it's different colors now.
Yes, you see, the liquid, as it starts up the paper toweling, is beginning to separate the black ink into various colors. And that's how you're going to decide whether A is ink or B is ink, and of course the other one being food coloring. Now, that takes a little while to separate them well. So let's see if we can investigate some of the reasons why this system will work. And what you're going to be doing is exactly the same thing that chemists do when they use chromatography to analyze chemicals and also to purify them. In order to do that, we have to think about molecules, because chemists deal with molecules all the
Yes.
time. What are the various forces that are on molecules? Problem number one.
Well, there are different,
All
different
kinds of different forces. Well, you notice that as the liquid is rising up here, that the liquid is going to get next to the dye.
Yes.
So let's see what happens when liquid molecules get near a soluble dye. We'll do that with my agitator over here. I think we've used this before, haven't we?
Yep, the good old molecule
Yeah,
machine.
the good old molecule machine. Well, I have all different kinds of molecules here today. These little black plastic balls in this water glass, what kind of molecules do you suppose they are?
Water molecules.
Okay, you put the water molecules in there.
Okay.
Go ahead, just pour it down. Okay.
There goes
Now,
the water.
that's the water. Now, here are our dye molecules, let's say. And I have little magnets inside, so they'll stick together, see, and attract each other like molecules do, see? So let's say those are our dye molecules.
Okay.
So you put the dye molecules into the water, too.
There.
Okay, now we put the top on. Now, what's the motor down here represent?
Heat.
That's heat. And when we turn it on, we're going to get this to vibrate up and down. And watch what the water molecules do to the dye.
They're hitting against them and separating them.
Yes. So that when you put a soluble dye into the water molecules bang away into it and break up the dye. They also weaken the force between the molecules, the dye molecules. But now, as these water molecules bang into the thing, you can see how they could push them along, couldn't you?
Yes.
Which is what they're going to do over there in the paper toweling. Also, watch what happens as I turn up the heat now and let some of the water molecules evaporate. Watch. Well, we won't wait for them all to evaporate. Now, you see what we have left?
Yeah, we have some dye molecules left, but
Yeah.
they're all broken up.
They're broken up, but notice how the blue could all lump together in one group, couldn't it?
Yes.
If we let the water go away, we'd have the dye deposited.
Uh-huh.
Okay, now let's see if we can illustrate that same problem over here with my stovepipe. Another kind of molecule group. See? Here's a stovepipe, and here, these magnets on here represent water. and they come from down below, and they're going up here, you see, just like the ones over there in the paper. Now, if that's true, we had a dye molecule here made up of different kinds of magnets. You could see how the dye molecule would get pushed up along with the water. See, the water molecules banging into it.
And pushes it up.
And would push it up. You could also see how when the water evaporated finally and flew off into the air, if I could take all these off, these dye molecules would be left behind.
Yes, and they'd be all separated.
Okay, now that's exactly what's happening here. Look. See that?
Yep.
Now, what kind of colors do you see now?
Well, there's the purple color, and there's a big band of green.
Yes. That's ink, isn't
That's
it?
ink.
Now look at the food coloring.
Well, there's purple, and there's blue on top.
Sort of blue-black sort of there, yes. That's the ink and the food coloring. Let's see how A and B are doing.
Well, on A, there's the purple and a band of blue.
Yes.
And on B, there's purple and a band of green.
Yeah. Have you any idea which is which now?
Well,
So
I
far?
think
Yes.
I think A is the food coloring.
You do.
Uh-huh. I think so because the colors match up.
Okay, then you're not going to put B into the drink? You're going
Nope.
to put A instead?
That's what I'm going to do.
Well, let's continue while we wait for this to go up because I want to examine some of the other forces that are involved. Molecules are different weights, aren't they?
Yes.
Well, I have some more molecules, this time balls of different weights. Here. See, here's 2 glasses of molecules. Which one is the heaviest? Scale here, you can put them on and tell, can't you?
Let's see.
See, you're a chemist now, getting the molecular weight of these molecules.
Better be sure.
Those are the heaviest. Okay, you put those down there. Those are the heavy ones and those are the light ones. Okay, now, would you put them here in the pan and mix them all up? Now that's like the dye, right?
Yes.
A combination of several different kinds of molecules, which may happen to be of different molecular weights. And now they're all mixed up. Well, now, if we could put that in water, the water molecules are going to vibrate these, aren't they? Bang into them.
Uh-huh.
And if they're free to move around, which ones should be pulled down the most by gravity? The light ones or the heavy ones?
The heavy ones.
Well, instead of putting them in water, I'm going to vibrate them with this vibrator. And you watch and see if that's true. Is that true?
I think so.
Yeah. Which ones are on the bottom?
Well, the heavier ones.
Pulled down there by gravity. So as soon as you move them around to allow gravity to work on them, why naturally it'll pull down the heavy ones. I'll turn it around. We'll see if it reverses itself. We put all the light ones on the bottom. There they go. A couple of those are magnetized, I think. Now watch, see if it'll reverse itself. Now, you want to hold that for a minute?
Okay.
Notice that some of these are down below, too.
Yes.
And that when you do it this way, that because these are all in motion, because of the heat, that you won't get a nice clear band sometimes. They'll mix in with each other.
Mixed up.
Okay, now, would you please go over to the stovepipe and show me what would happen with the molecules as they were traveling up the paper?
Well,
See, this molecule is made of a heavy and a light one. Tell me now, if gravity is going to do our separation, where would they go?
Well, let's see. If these were the, let's see, if the round ones were the heavy ones,
Yes.
they would be down here, about like that.
Mm-hmm.
And if these were the lighter ones, they'd be up here, like this.
That's right. So you can see now, when chemists know what the molecular weight of the various chemicals are, they can design a kind of column so that they could have the heavy ones down below if they wanted. If they wanted them the other way, they could turn it upside down, couldn't they? And these would be down below, and the other ones, this would still stay down below, regardless of which way they turned it in this case.
Yes.
But they could have the liquid come from down here. And that would pull this down from this side. So they could have them in whichever way they wanted, depending entirely upon their knowledge of the weight of the molecules. Okay, how about our tests over here? If if it is true, and I'm not sure that it is in this case, that this one is red and green, right?
Yes.
Green up on top, red down below. Which do you think would be the heaviest molecules?
The red ones.
Yes, the ones in the bottom. Well, as I say, I don't think it's true, because when I try this in any direction, the red is always in the same direction as this, so I don't think it's necessarily heavier. But anyway, what about this one? Now you have sort of blue and red, right?
Blue and red.
Blue on the top and red below.
On the bottom.
And so which is the heavy one?
Probably the red.
Okay. Now, you're still going to keep, you're going to put A or B in the drink?
A.
You sure?
Still A.
Still A? Okay. All right. So now we've seen thermal, or the water molecules, and the heat molecule, or heat in general, making molecules move around. That gets them free to move. And we've now seen that gravity could pull down on some more than the others.
And that could separate them too.
That could separate them too. Now, you remember that water drop I was experimenting with over there? I said that that was going to help you decide a matter of life or death?
Yeah.
Okay. Well, now let's go and do it, and I'll show you why I said that. Because one of the other forces that there are on molecules is electrical forces.
Electrical?
Yes, electrical. Now, you see down here? Here's the slide that I'm going to put into the projector. And I have 4 surfaces on which I'm going to put a drop of water with this hypodermic syringe, see, by putting it on here like this. Glass,
Glass.
a piece of brass screen with all kinds of little holes in it, and I'm using that to compare here to a piece of paper towel, which has all kinds of little holes in it too. And finally, a thin layer of lycopodium powder. We've used that before. Remember,
yes.
that's a very interesting kind of powder that's very slippery. So I'm going to put 4 drops on here. And I want you to tell me, after you look at the drops as I put them on, something about the electrical forces of attraction between the water drops and the 4 surfaces. Wait, I want to turn my slide around. I got it backwards. Okay, now there they are. Pushed them in position. Now I want to take my pencil and straighten them all out so they're all nice and even. Right there's the glass. See? Now I'll take the hypodermic syringe and put a tiny drop of water of a very measured size right there. Now let me focus it so it's nice and sharp. Now, remember, as I was holding the hypodermic needle up here like this, the drop was kind of round, like but now look at it. Why is it like that?
Well, because it's hugging the surface of the glass. It's attracted by the glass.
First of all, gravity is pulling down on it, and that would make it flat, wouldn't it?
Yes.
But you could also see that if the water drop and the glass attracted each other more, it would be pulled down even further, wouldn't it?
Uh-huh.
Okay, so now let's use that as our standard, the attraction between water and glass. The next one was the piece of brass screening. I'll put a drop on that and see if you can tell me about the attractive force between that metal and water. What do you mean?
Well, there's not much of an attractive force.
How do you know?
Well, because it's almost a perfect circle there.
Well, it's flat on the bottom.
Yes, but it's not being pulled down as much as the water on the surface of the glasses.
If it were pulled down as much, it would be flat like this, wouldn't it?
Yes.
So obviously it isn't pulled down. Gravity should be the same because they're both the same size drops.
Uh-huh.
Okay, very good. So now you can see that water is attracted to those two things with different amounts. What was the next one over here, you remember?
Paper towel.
Okay, one tiny drop coming up on paper toweling.
Wow.
Matter.
That one went right through.
Now, what do you expect that the force between the molecules of the paper and the glass and the water are like?
Well, I think that they're attracted quite a lot.
Yeah. Well, that's probably true, but I want to point out also that there are a lot of bigger holes in here, so the drop could sink in.
Yes.
But obviously the drop didn't stay up on top. There were holes in this brass too, weren't there?
Uh-huh.
So you could probably say that the water and paper attract each other quite a bit. Now, remember that? See that little bump on the end? What was that?
that was that
Like,
powder.
lycopodium powder, all right? 1 drop of water on lycopodium. Would you say that's more like the paper or more like the brass screen?
I'd say that's more like the brass screen.
Yes, in fact, yeah, go ahead, why?
Well, when you first let it drop, down, it bounced off almost.
In fact,
So,
I'll shake the projector a little bit. You watch it.
it's wiggling back and forth.
Yeah. Now look at the drop behind your head there, the brass one. It's
That
not
one's
moving
not.
at all, is it?
No.
While the other one over there is rolling. So the reason I did this, Al, I wanted you to see that water is attracted to, and molecules of various things are attracted to water in varying amounts. So that you could see now, as we let the water go up through the paper towel, various kinds of chemicals are going to be attracted with various differences in forces, aren't they, to the water?
Yes.
If they're attracted strongly to the water, won't they be carried up higher?
Uh-huh.
And if they're attracted weakly,
Then they'll be...
they deposit it first, right? Okay. Well, now, let's turn the projector off here. And you remember that stovepipe over there?
Yeah?
You come on over and separate the molecules now according to the electrical charges, let's say. Let's say that the square ones here are attracted to water the least, while the round ones are attracted the most. How would you put them up?
Well...
The square ones are attracted the least, and the round ones are attracted the most.
Put the round ones up here. Like that. And the square ones down here. Because,
Why?
well, these are attracted to the water the most. And these...
What?
No, these are attracted to the water the most, and these are attracted to the water the least.
You can see then if there's a lot of water here, as it's going up, these that are going to have the least attraction would be deposited first.
Uh-huh.
Right? And these would be carried up further and further. Very good. Well, now let's make the, what kind of assumptions can you make about your, let's say, ink, for example? If this were the case with the ink, which would be it? Here's the blue, here's the red. Which would you say was attracted to water the most?
The green. The green up top.
Greenish, I call it blue, you call it green. It's kind of a greenish blue,
Yeah,
okay?
both.
And how about the food coloring?
The blue.
Yes, the blue up there. By the way, is it still A or B, which?
Still A.
Yeah, still A, you sure?
A, uh-huh.
You're sticking with A. All right. Well, now, I think we're about ready to try it. Are you?
Well, I guess so.
Okay, but before we do that, I want to go around and show you now how you want to set this up at home, because I think it's sort of a lot of fun, and I want you to be sure to remember how to do it. What did you do? Get a piece of toweling.
Uh-huh. And put it in a tube with tape.
Now, I folded this down in here so it make it a little stronger, so it was a little, so it wouldn't collapse so fast. There's tape along here to hold it together. And now take a clean
Pen or brush.
or brush. Go ahead.
And
And what do?
you dip it in the substance, whatever you're using.
Whatever, and let's put it in the ink,
Okay.
which is what you think is.
B, I think.
You think it's B? Okay, take B. And
Right.
put it up now so it won't touch the water,
an
about
inch.
or so, yeah.
And you make a line all the way around the tube, like that. There.
Okay, and then what do you do?
Then you put it in a solution, which is water and alcohol.
Yeah. 5 parts of water,
And
and
1
part of alcohol. Okay, you want to put it in that one marked ink?
Okay, put it in there.
Now, when chemists do this, well, here, let me take this one right here. You see, if you had this, for example, and this chemical right here was the one that you were interested in, you see how you could cut out that little piece of paper, and you could now analyze the chemical on it.
Uh-huh.
You could also, if you wanted to make it very pure, you could take that little part, cut that little part out there, dissolve that in water again, and do the whole thing again. It would separate it even more, so that you could
And
get
you could
very
keep
pure
going.
chemicals this way. And it's called chromatography. Well, I'm taking these out because I want to open them up for you to make sure that you are going to do, take the one that you want. Here's A. And B, let's move them out of the way for the time being, because I want to open these up for you to make sure to see whether you can B.
B. And that's food coloring. And A. And then ink.
All right. Now, what I want you to do is to match A and B with ink and food coloring by looking at the colors.
Well, I still think that A is the food coloring because there's the purple down below and there's the blue on top.
Yeah.
And on the ink,
Here.
there's the
Shall I move the ink? You
Yeah.
want to put it over like that and like that, huh?
because
Okay.
the ink and the B have the red and the green on top.
Here's all both green.
Green.
Here, these are both blue.
Blue.
Here are the red down below here. But here is a mixture. You see it, how it's kind of dark in there? Okay. Now, what you want to do is let these dry to be sure to increase the contrast because there's water in here. And I did this before. I repeated exactly what you did, and I took the results and put them on a board and let them dry. See? Now you see the contrasts are much better. You can see the edges on here.
Yes.
From my previous test, which one are you going to select?
A for food.
A is like this one for food, huh? While ink and B are alike. So you're definitely sticking with A now.
Yep.
All right. All right.
And I'll soon know.
Okay. Here's the liquid. And you want to take what?
A.
Okay, a nice big eyedropper full of A.
There it
Okay,
goes.
that should do it.
Oh,
Now remember, if you've made a mistake,
I'm dead.
you're dead. Or, well, at least you're going to turn a terrible shade of blue. Go ahead and try it. You all right?
Am I blue?
Just your lips. Anyway, when you do it, you chose the right one. I want to congratulate you because you now have used paper chromatography to solve a rather difficult chemical question. And if you want to do it at home, do it like this and have a lot of fun with chromatography.
Watch Mr. Wizard is presented each week at this time by the Public Affairs Department of NBC News in cooperation with New York University.